नमस्कार, आप सभी का स्वागत है। मैं हूं राहुल और आप देख रहे हैं PMeVIDYA चैनल्स और NCERT का ऑफिशियल यूट्यूब चैनल। आप सभी जानते हैं कि आज शुक्रवार है और हर 2 सप्ताह के बाद हम शुक्रवार को सुबह ठीक 10 बजे आपके लिए एक वेबिनार सीरीज लेकर आते हैं, एक वेबिनार श्रृंखला लेकर आते हैं जिसका शीर्षक हमने रखा है सुने और सीखें। इसमें विभिन्न विषयों पर हम आपके लिए वेबिनार लेकर आते हैं। उसमें एक एक्सपर्ट होते हैं जो अपनी राय रखते हैं और एक वृहद उनका जो ज्ञान है, जो उनका अध्ययन है, वो आपके साथ साझा करते हैं। सो इन टुडेज वेबिनार सीरीज लिसनिंग टू लर्न, वी हैव दिस सेशन 44 स्निपेट्स फ्रॉम एंशिएंट इंडियन मैथमेटिक्स। दिस इज द टॉपिक ऑफ डिस्कशन एंड लर्निंग इन टुडेज लिसनिंग टू लर्न वेबिनार सीरीज। आप सबका एक बार पुनः स्वागत। चैनल नंबर 9 से लेकर 12 तक आप हमें देख रहे हैं। आप भी हमारे इस लाइव इंटरैक्टिव सेशन का हिस्सा बन सकते हैं। आप चाहे तो हमें 8800440559 पर हमें फ़ोन कर सकते हैं या हमारी इस सेशन की ईमेल आईडी। चलिए, अब मैं ज़्यादा आपका समय नहीं लेता हूं क्योंकि जब एंशिएंट मैथमेटिक्स की बात होने वाली है तो जाहिर सी बात है कि कुछ ऐसे लोग भी होंगे हमारे साथ जो बहुत ज़्यादा जिज्ञासु हो गए होंगे, क्योंकि गणित हमेशा से एक ऐसा विषय रहा है जिसने आप सबकी जिज्ञासा को बढ़ाया है। तो मैं बिल्कुल आपका समय नहीं लूंगा और अपना कार्यक्रम शुरू करूंगा। हमारे साथ स्टूडियो में है डॉक्टर गगन गुप्ता। सर नमस्कार, आपका बहुत बहुत
नमस्कार राहुल जी।
आप NCERT में ही अपनी सेवाएं दे रहे हैं और मैं आपसे गुजारिश भी करूंगा कि आज जो हमारे एक्सपर्ट हैं उनसे न सिर्फ परिचय कराएं हमारे दर्शकों का, बल्कि उन्हें बताएं कि आज वो जिस ज्ञान परंपरा की बात करने वाले हैं वो कितनी कीमती और कितनी हमारे लिए उपयोगी है।
धन्यवाद राहुल, बहुत बहुत धन्यवाद। आज हमारे साथ पुणे से दोस्तों जुड़ रहे हैं डॉक्टर शिराली, डॉक्टर शैलेश शिराली, जो कि आपके साथ अभी बात करेंगे एक बहुत ही महत्वपूर्ण विषय पर, स्निपेट्स फ्रॉम इंडियन एंशिएंट मैथमेटिक्स। दोस्तों, आदिकाल से ही मानव का स्वभाव अपने आसपास की चीज़ों को देखने में रहा है और भारत में एस्ट्रोनॉमी को लेकर काफ़ी काम हुआ है, एस्ट्रोनॉमिकल साइंसेस को लेकर काफ़ी काम हुआ है और उसके बाद गणित जैसे विषय में विकास की और नई नई प्रमेयों के उद्धरण की एक लगातार प्रक्रिया देखने को मिलती है। आज मेरे साथ डॉक्टर शैलेश शिराली हैं, वो जो राजगुरु नगर पुणे से हमारे साथ जुड़ रहे हैं। वो इस विषय पर आज हम सबसे बात करेंगे और अपनी बात कहेंगे। दोस्तों, ये श्रृंखला अगस्त 2021 में शुरू हुई थी। कोरोना काल का समय चल रहा था और उस समय हम सब लोग काफ़ी डिप्रेशन में थे। ये श्रृंखला उस समय शुरू हुई, रश्मि कुलकर्णी जो कि कतार से हमारे साथ जुड़ी थी, और उसके बाद इंडियन प्लेनेटरी मिशंस, इंडियन मैथमेटिकल साइंसेज, मेडिसिन, मैकेनिक्स, विंड टनलिंग एट्सेट्रा 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 इशूज़ पर हमने चर्चाएं की हैं। और इस पूरे प्रोग्राम की प्लेलिस्ट आपको हमारे NCERT यूट्यूब ऑफिशियल चैनल पर और साथ साथ ncert.nic.in जो हमारी आधिकारिक वेब सीरीज है उसके इवेंट सेक्शन में आपको मिल सकती हैं। आप सब लोग अपने सुझाव हमें देते रहें। आपके सुझाव हमें इस श्रृंखला को आगे बढ़ाने में काफ़ी मददगार, काफ़ी सहायता प्रदान करते हैं। आप अपने विषय, पसंद के विषयों को आप हमें ज़रूर बताएं। आपके पास हमारे ईमेल्स हैं, आपके पास हमारा टेलीफोन नंबर, जैसे मेरे साथी राहुल अभी बताया था। साथ ही साथ आप हमारे यूट्यूब चैनल NCERT ऑफिशियल पर इस प्रोग्राम को लाइव देख रहे हैं और आप वहां पर भी आप अपने सुझाव हमें भेज सकते हैं। आप अपने प्रश्नों को ज़रूर पूछें। हम इन प्रश्नों को इस कार्यक्रम के आज के सत्र के आखिर में समावेशन करेंगे और डॉक्टर शिराली से उन सारे प्रश्नों पर काफ़ी लंबी चर्चा करेंगे। दोस्तों, अब मैं आपका परिचय कराता हूं डॉक्टर शिराली के साथ। डॉक्टर शिराली is presently the Director of Sahyadri School, which is an organization with the Krishnamurti Foundation of India, popularly known as KFI, Pune. Dr. Shirali has earlier served as principal of Rishi Valley School, which is a very famous school in India, which is also again associated with the KFI. Dr. Shirali is a trustee of the Krishnamurti Foundation of India and has been involved with the Krishnamurti School since 1983. He has also been in the field of mathematics education for more than 3 decades and has been closely and vitally involved with the Mathematics Olympiad movement in India since its inception in 1980s. Dr. Shirali is the author of several mathematics popular books for high school students, namely Adventures in Problem Solving, a primer on number sequences, First Steps in Number Theory, a primer on logarithms, Adventures in Iteration, which has come in 2 volumes, and Arithmetic and Algebra, Numbers and the Beginning of Algebra. With this title itself, we can understand that how deep Dr. Shirali has been in the mathematics, in the development of mathematical texts in country. Dr. Shirali has also served as chief editor for the magazine At Right Angles, which is published by the Azim Premji University, Bangalore. He has a particular interest in ancient Indian mathematics. He also has a deep interest in nurturing and facilitating inquiry into fundamental issues among teachers and students at the school level. Viewers, आज का ये जो प्रोग्राम है हमारे पूर्व में दिखाए गए कुछ प्रोग्राम्स की श्रृंखला में ही आगे है। आप याद कीजिए जबकि हमारे साथ आईजर पुणे से केपी मोहनन मिले जुड़े थे, इंडियन इंस्टीट्यूट ऑफ साइंस से वहाँ के वैज्ञानिक हमारे पास नंबूदरी जी जुड़े थे और उन लोगों ने भी रीजनिंग ऑफ मैथमेटिक्स, रीजनिंग एंड एब्स्ट्रैक्ट थिंकिंग के ऊपर बात की थी। प्रोफेसर शिराली, आपका इस फोरम पर स्वागत है। हम कृष्णमूर्ति फाउंडेशन ऑफ इंडिया के बहुत थैंकफुल हैं, ग्रेटफुल हैं कि उन्होंने हमारे साथ एनसीईआरटी के साथ इस कार्यक्रम के लिए कोलैबोरेट किया। आपका बहुत बहुत धन्यवाद। एंड नाउ दिस फोरम इज फॉर यू सर, प्लीज।
Namaskar and thank you very much for this invitation. I am very grateful to the NCERT. So, students, I am going to describe to you 4 problems today, 4 fun problems. I feel very strongly that in mathematics we need to study fun problems, and these fun problems are even more fun when you see that they have a long history behind them and they are associated with puzzles and things that you see in daily life. Because I believe that in ancient India, mathematicians had a very great love for recreational mathematics, what we today call recreational mathematics, mathematics which you meet with in puzzles and little problems. So I have described them here as some gems from ancient Indian mathematics. And I've written here there is great beauty and richness in these episodes. And I think that mathematics should be taught with a feeling for that history. So let me plunge into these things right away. The first one I'm going to talk about is about magic squares, something which we all know, and as I've written out, the magic squares have been known since very ancient times, probably at least 2,000-3,000 years, and they are still a source of great pleasure. So let me ask my first problem, which is, suppose you make a 3x3 magic square using the numbers 1 to 9. What is the number that is right in the center of the square, the middle square? Well, I'm going to give you the answer right away. It is, in this particular magic square, it is 5. But one very interesting question is there a possibility of making a magic square with some other number in the center? Can it be any other number? So look at this reasoning. If you add up the numbers from 1 to 9, you get 45. And 45 is divided into 3 rows, so each row must be 15. So the magic sum of the magic square is 15. Suppose you call the middle number to be m. Then m is one of the numbers from 1 to 9, obviously. Now you consider the various possibilities. Just look at this diagram. Supposing it is 9, supposing you imagine that this is 9. Now somewhere around here, you have to have an 8, because 8 is one of the numbers, but then 9 plus 8 is already 17, and you can't possibly get 15 because you have already gone beyond 15. So it cannot be 9. For the same reason, it cannot be 8, because 8 has got a 9 somewhere around it, it won't work. 7 also has somewhere a 9 around it, it won't work. 6 also will not work. Now you start from the other end. Suppose you put a 1 out here. Now somewhere around it there is a 2, and 1 and 2 add up to 3, which means the remainder has to be 12. But 12 is too large. There is no 12 in this set. So it can't be 1. And for the same reason, it can't be 2, 3, 4. So look at this interesting piece of reasoning. It cannot be 9, 8, 7, 6, and it cannot be 1, 2, 3, 4. Therefore, it must be 5. And once you know that it is 5 and you know that the magic sum is 15, it's quite easy to construct this. I'll leave it to you. You will just play around with this. And Here's another way of doing it, just for interest's sake. Supposing you draw 4 lines like this through the square, all of them through the central square. Now the total of these 3 numbers on this line is 15. The total of these 3 numbers is also 15. These 3 also 15. These 3 also 15. So since there are 4 lines in all, the total is 60. Now the central number, you'll notice, is there on all 4 lines, so it is covered 4 times. And the rest of the numbers are covered exactly once each, which means that you can write this equation that 60, which you got out here, is equal to the sum of all the numbers in the whole square plus 3 times the number which is in the middle, because that the extra number of times it got counted is 3. Right. So you get 60 is equal to 45 plus 3 times m, and that gives you m equals 5. We solve that equation. So here's an example of a magic square which goes back to ancient India, in which you'll find it's difficult to say who is the person who actually made these things. But the person has tried to put 4 such magic squares. You'll notice all of them have got 5 in the middle of the square, and he has put 4 such squares together to try to make a 6 by 6 magic square. Okay, I'm going to move on now. So here are some interesting points which teachers may want to make. One is it's impossible to have a magic square of just 2 by 2. The other is, notice how we proved the first proof that the middle number is 5. We proved it by what is called exhaustion. That is, we looked at all possibilities and then eliminated everything which did not fit. So you got only one thing which was left. There was also an algebraic proof in which you solved an equation, which is a more sophisticated proof. You'll also notice that in this square, there are arithmetic progressions which pass through the middle of the square. I didn't talk too much about it, but you'll notice all these are arithmetic progressions: 159, 357, 456, 258. So a number of arithmetic progressions are there. And you have ideas of symmetry. So it's very nice. It's a very interesting object to study because you get to know about ideas of mathematics through this, the idea of symmetry. And one interesting exploration which students can take forward is, can you have a magic rectangle? Why only magic square? But I'll leave these questions for you to look at. Now I'm going to move to magic squares of order 4, which are much more complicated than magic squares of order 3. And one very interesting property that they share is this. First of all, it's much harder to make a magic square of order 4. I invite you to try. And if you'll find that whichever way you make a magic square, they have this property that if you call these 2 corner numbers A and B, and these 2 middle numbers as C and D, then this is always true, that A plus B is equal to C plus D. And it's a very nice thing to try to prove it. It's not easy to prove. So try it sometime. It's a very nice problem. And it's true for each pair of symmetrically placed rows and columns. So for example, what is in this square plus what is in this square will be equal to this plus this. You'll notice the symmetrically opposite. Similarly, what is in this square plus what is in this corner will be equal to this number plus this number, and so on. It's all very nice symmetries in it. Here are 2 very famous magic squares from history. This is one Renaissance painter, European Renaissance painter. Why he put a magic square here, nobody will know. It's a mystery. It goes back to the 16th century, long back. And this is a Jain temple in Khajuraho. Again, why have they put a magic square there? It's very difficult to go back into the mind of the people and understand this. And I've shown the actual magic squares here. So I hope you can read the numbers from your screen there. 16, 3, 2, 13. 4, 15, 14, 1. You'll notice if you want to see, 16 and 13 is 29, and 15 and 14 is 29. Similarly, 16 and 1 is 17, 11 and 6 is 17, and so on. All the symmetries are there. And look at the one here. Same, all the principles of symmetry are there here also. Very beautifully done. This goes back to the 10th century. And here are the I've shown it to you, and I've put the actual numbers here. So you'll notice those properties here. Look at 7 and 14, 21, 15 and 6 adds up to 21. 9 and 14 is 23, 13 and 10 is 23. And so all these symmetries are there. And why these symmetries hold is a beautiful problem to try to prove. So try it sometime. Now this, between these two, I'm going to show you that this Khajuraho square has additional properties. Not only is it a magic square, it is magic in a very special way. That's why I've called it truly magical. So look at this. Look at the numbers. I've written the same square in twice here. I've highlighted some numbers in red. 6, 10, 11, and 7. So first of all, I forgot to say that the magic sum of this particular square is 34. Since you have the numbers from 1 to 16, so this magic sum naturally has to be 34. When you add up all the numbers from 1 to 16 and divide by 4, you will find you get 34. So you get 34. Now you will find for this, for example, for this 7 and 12, 19, and 1, 20, and 14, 34. So everywhere it is 34. Now you'll find that these 4 red numbers are also adding up to 34. And how would you describe this here? You go from 6 to 10 to 11. If you were to continue here, you sort of fall outside the square, but then it goes back again here. So there's a kind of wraparound which is throughout here. So that means these are called broken diagonals, and the broken diagonals with wraparound also add up to the magic sum. Similarly, look at this. 1 and 11 is 12. If you go outside, it will fall outside here, and you will come here. So 12 and 16 is 28, and 6 is 34. So this broken diagonal also adds up to 34. So you'll find that if you look at this Khajuraho square very carefully, every possible broken diagonal also adds up to the magic sum. And these kinds of squares are known as pan-diagonal magic squares, or simply pan-magic squares. And it's the really interesting question is how did these mathematicians have so much interest in these things? And then look at this. I'll show you another thing about this. Take any 3 by 3 square in this here, like let's say this one here, and look at the corner squares. 2 and 15, they add up to 17. 8 and 9 add up to 17. 12 and 5 add up to 17. 14 and 3 add up to 17. 7 and 10 add up to 17. 1 and 16 add up to 17. So it has all kinds of properties, this magic square. So one of the people who did pioneering work in this field was the mathematician Narayana Pandit, who belongs to the 14th century. And he wrote a book called the Ganita Kaumudi, in which he described how to construct magic squares of many different kinds, not only squares, but also rectangles, hexagons, and so on. And moreover, he also showed how to construct all possible pan-diagonal magic squares of order 4, like the one which you saw in the Khajuraho temple. And moreover, it's a very interesting combinatorial problem. Can you count the total number of such squares if I only insist that you use the numbers from 1 to 16, how many pan-diagonal magic squares are there? And Narayana Pandit computed it and wrote it as 16 times 24, and the answer is 384, which is correct. It turns out that you can actually prove that by an advanced method that the answer is 384. Exactly how Narayana Pandit proved it, we don't know. But it's a very nice challenge to prove it. Just as before going on, I want to say this, that in those days, magic squares were not learned only for fun purposes. They even had they were truly considered as magic. So for example, he says in his book that I am making these to destroy the egos of bad mathematicians and for the pleasure of good mathematicians. And look at this. If magic sum of, when you have a magic square of sum 20, whose magic sum is 20, it can be used in cases of food poisoning. Magic sum is 28 when your rice field is attacked by insects. When the magic sum is 84, can be used to quieten children when they are crying. So it's very interesting to see this, that that they really believed that these magic squares had magical properties. And I think this is something very important we need to study. And just before finally moving on, so this connects up with one very important topic in higher mathematics called topology, because you'll notice that the pan-diagonal squares, it's like when you go across a row, it curves back onto itself from behind. So that is what this kind of a shape. This is called a torus in mathematics, or a donut shaped, or a vada shaped. Okay, so I'll move on now. Next topic I'm going to talk about is Fibonacci numbers. Some of you may know about the Fibonacci numbers, a very famous sequence. Fibonacci was an Italian mathematician of the 11th century, 12th century rather, and he was very important for the development of European mathematics because he was one of the people who introduced the Indian Arabic system of numeration to Europe. Till then, they were just using, what are called Roman numerals and so on. And now, these numbers, which are now known as the Fibonacci numbers, 0, 1, 1, 2, 3, 5, 8, and so on, in which each number is the sum of the previous two. So, for example, 13 is 5 plus 8, 21 is 8 plus 13, 5 is 3 plus 2, and so on. So, that's called the Fibonacci sequence. And you'll notice that I have constructed it using an arithmetic rule. Right? So I've added two numbers together to get the next number. So it's like you're doing arithmetic on this sequence. But it turns out, very surprising, that these numbers can also be obtained using a combinatorial situation. And I'm going to show that to you. So first of all, to introduce it, I'm going to introduce the idea of a composition, in which I'm going to ask, in how many ways can you write any number as a sum of smaller numbers? Okay, I hope you. So for example, look at 3. 3 can be written as 3 itself, or 2 plus 1, or 1 plus 2. And so you'll notice the order which we have used, it matters. 2 plus 1 is regarded as different from 1 plus 2, or 1 plus 1 plus 1. And that is all the ways possible. So you'll notice there are 4 ways. So supposing I write, so these are called the compositions of 3. So in the case of 3, there are 4 such compositions. Let A subscript n, A of n, be the number of different compositions of n. So A3 is 4. Now, can you find a formula for A of n? That's the problem. Now, this is not the problem which Fibonacci studied and which is also going to come up in ancient Indian mathematics, but I'm going to introduce the problem through this. Okay? Now, you get a very nice pattern when you try to actually construct the table. So 1, if you take 1, the only composition of 1 is 1, so A of 1 is 1. Take 2, you can write it as 2 or as 1 plus 1, so there are two such compositions. For 3, we already saw it, there are 4 such compositions. For 4, you have 4, 3 plus 1, 1 plus 3, 2 plus 2, then 2, 1, 1, 1, 2, 1, 1, 1, 2, and 1, 1, 1, 1. And if you count these, there are 8 such things. And if you go through the calculations for 5, I have listed them all here, you'll find there are 16 out here. And you immediately see 1, 2, 4, 8, 16, a beautiful sequence. Anybody will spot the pattern, that it seems to be what is called a doubling sequence. It seems to be that A of n is 2 to the power of n minus 1. And this is a very important step in mathematics, that at this point, it is not a theorem. You have not proved anything. It's only a conjecture. And it's exactly like in science. We notice a pattern, and then we make a conjecture based on that pattern, and then we try to prove that conjecture. So let's try to prove it. And the method of proof is very interesting. Now let's start by looking at the compositions of n in which there is only one number used. That is n itself. So obviously there's only one such. Now let's look at compositions which have more than one term. Suppose you call k as the first term. So n is equal to k plus something else after k. Now what do those other things add up to after k? If the first term is k, then the rest of it must add up to n minus k, because the total is n. All right? And now this k can be anything from 1 up to n minus 1. And you can combine each of these values with all possible compositions of n minus k. Right? So this, if you think about it, this leads to a very nice equality. Since that bracketed part a plus b plus etc. is a composition of n minus k, you get this very beautiful equality here. A of n, this corresponds to all the compositions in which the first number is n minus 1, because then the rest of the numbers add up to 1, so there's only a1 such compositions. Then these correspond to the first number being 2. And the rest of the numbers add up to n minus 2. Sorry, the first number being n minus 2, and therefore the rest of the numbers adding up to 2. And similarly, all the way up to n minus 1. So a of n is equal to all this. Now from here to here, from here to the second last term, if you notice this, if you replace n by n minus 1, you get a of n minus 1 is equal to the same kind of sum, except that it stops one term short. Instead of going up to a of n minus 1, it stops at a of n minus 2. Which means that from here to here, it is the same as this. So you look at, you arrive at this beautiful thing, that a of n from here to here is just a of n minus 1, and then again another a of n minus 1, and the two, that means two which are identical pieces. A of n is equal to this plus this, so you get a of n is equal to 2 times a of n minus 1, which means it's a doubling sequence. Each term is exactly double of the previous one. Achha? So you see that beautiful pattern which we proved, which we noticed, conjectured, is true. So we have managed to prove that a of n is indeed equal to 2 to the power of n minus 1. Now let's come to the Fibonacci numbers. So the topic comes up when you consider the mathematics of poetry. And in poetry, there is one technical term called prosody, which is about, the rhythm of the poem. How many syllables there are in each line, because a poem has to be balanced. Balance is very important in the poem. So this is a problem which has been studied way long back by grammarians like Pingala, by Virahanka, Gopala, and one important mathematician called Hemachandra. Gopala and Hemachandra, they are both of the 12th century. So they looked at this problem in which each syllable is, you categorize syllables as two things. Either they are short or they are long. Or actually they use slightly different words. They called it light and heavy. But for simplicity, we are calling it short and long. So short is considered as having length 1. Long is considered as having length 2. So this is S, this is L. And words can be formed using S and L. So how many words can you have which have length 1? Well, the only possible word is S. Exactly one word. How many words are there with length 2? Now you can have either L, because L has got length 2, or you can have SS, which also has length 2, 1 plus 1. So there are 2 words of length 2. So here's a very interesting combinatorial problem, which was studied by Hemachandra and Gopala in the 12th century. How many words can you find which have got a total length of n, where length is defined in terms of these 2? So they were interested in this because it comes up in Sanskrit poetry, this whole question. So let's call this number as C of n. And just like the compositions problem, we'll analyze it in the same way. So words of total length 1, well, there's only one such number. Words of total length 2, you can have L or SS. There are 2 such words. Words of total length 3, you can have LS, right, 2 plus 1, or SL, which is 1 plus 2, or SSS, 1 plus 1 plus 1. So there are 3 such words. Words of length 4, LL, right, 2 plus 2, or LSS, 2, 1, 1, which add up to 4, or SLS, 1 plus 2 plus 1, or SSL, all of which add up to 4, or SSSS. And you'll notice there are 5 such possibilities. And if you go on to 5, you'll find there are 8 such possibilities. For 6, there are 13 such possibilities. And look at this sequence. What a beautiful sequence it is. 1, 2, 3, 5, 8, 13. Exactly the numbers which we usually call the Fibonacci numbers. So this sequence was spotted by Hemachandra, and they worked out that it must satisfy this combinatorial property and the arithmetical property, that each number is the sum of the previous 2. Now mind you, we have still not proved anything. We have made a conjecture that the total number of words of length any particular number is always a Fibonacci number. So let's see how we can prove it. So this is what we see. So the observation is that this is a displaced Fibonacci sequence. Why displaced? Because it doesn't start with 0, it starts somewhere later. So how do we prove this? Exactly the same kind of logic. Consider all words of total length n, where n is some number greater than 2. Each one either ends with s, you look at the last syllable. Either the last syllable is s or the last syllable is n. Imagine that you hide that last syllable. So you sort of delete it. That means the leftover word, what will be its total length? Since you have removed 1 or 2, it must either decrease by 1 or decrease by 2. So if the deleted letter is s, the modified word has length n minus 1, or else it has length n minus 2. And in each case, you get all possible such families. So for example, look at the case for n equal to 5. There are 8 words altogether, that table that we made. These which I have marked in red are those which end in s, and these which I have marked in blue are those which end in l. You'll notice that there are exactly 5 of these here, and there are 3 of these here. And if I remove that last letter, that last syllable, you will find that you get LL, LSS, and so on. These are all the words whose total length is 4 or total value is 4. These are all the words whose total value is 3. So you see, the fact that there are 8 altogether is coming from the fact that there are 5 here and there are 3 here. So you can see why each number is the sum of the previous 2. It follows because of the same kind of logic as happened last time. And the first 2 numbers coincide with 2 consecutive numbers of the Fibonacci sequence, 1 and 2. So therefore, every successive number must be a Fibonacci number. And therefore, the C sequence is just a displaced sequence. So as I said, these numbers are called the Gopala Hemachandra numbers, and they discovered these numbers much before Fibonacci, at least a century before Fibonacci. And I just make these points before moving on, that you'll notice how when we generated this sequence, we generated it observationally. It was very much like doing an experiment in a laboratory. We generated the sequence empirically. After that, if we are to get some information and pattern from it, we must organize the data correctly. We must organize the data as efficiently as possible. That's also part of mathematics. Knowing how to organize data is also part of mathematics. Spotting a pattern in the data, you spotted the pattern that either each sequence is a doubling sequence or that each number is the sum of the previous 2. And formulating a conjecture very precisely in algebraic language, that's also part of mathematics. Then we proved the conjecture using a very important technique called recursion, where we looked at how each number is related, how each configuration is related to the smaller configurations. And just as a, by the way, I may say that for the Fibonacci sequence, there's no simple formula for the general term of a Fibonacci sequence. There is a formula, of course, but it's a rather complicated formula and not easy to find. Okay, let me move on now. I'm going to talk next about an algorithm which goes back even further back in time to Aryabhatta. And I'm going to illustrate it through a problem which is sometimes you often seen in as a puzzle problem. So the actual problem that Aryabhatta considered was this. Suppose you've got integers a and b and c, and we want to solve this equation, ax plus by is equal to c. But we are not interested in just any solutions, but in integer solutions. That is, they must be in the values of x and y that we get must be integers. Now, so he had found an algorithm to solve it, and it's a famous algorithm which is called the Kutaka algorithm, in which basically Kutaka means to pulverize, to break up and make something smaller. So it's like banging something and in the spices. So you'll find that that algorithm, if you translate it into mathematical symbols, it is very similar to the algorithm used to find highest common factor, or also what is called GCD, greatest common divisor, which is sometimes known as Euclid's division algorithm. The two are almost very similar algorithms. And it can be used to solve a famous puzzle, which I'm going to show you here. Supposing you have jugs, a jug of capacity 3 liters and a jug of capacity 5 liters. And you have a tank of water with as much water as you feel like. I want to use those jugs to measure exactly 1 liter. At the end, one of the jugs should have exactly 1 liter. And there is no estimation allowed, no fractional filling permitted. And of course, 3 and 5 is just a particular case. The general case is replace 3, 5 by a comma b, where a and b are some positive integers. And you'll find as a surprise fact that this puzzle actually played a part in a Hollywood thriller. Some of you may try to guess which is this Hollywood thriller. I'll tell you later. So here is the algorithm given by Aryabhatta to solve this particular problem. So this, in which he tries to solve ax plus by is equal to 1, not generally c, but you can always scale it up and get c. And if you translate, now this is written as a shloka. If you translate this into mathematics, it is given any two co-prime integers, co-prime positive integers a and b. Co-prime means they have no common factors. So a is greater than b. Replace a and b by b. So the second number comes in front, so it's b. And the first number is, second number is replaced by the remainder when you divide a by b. Okay, so a divided by b remainder. Now, having got this new pair, repeat the argument. So now you've got a smaller number and a still smaller number. Do the same thing to the new pair. Again, you will get numbers which are still smaller. So you'll notice that's why it is called the Kutaka. It is, you're continuously doing this operation, repeatedly doing this operation, so that it becomes smaller and smaller and smaller. And finally, you can retrace and get the solutions to ax plus by is equal to 1. So I've given an example here. We're going to try to solve 10x plus 7y equal to 1. So let's see what we do. 10 comma 7, we replace by, so that 7 comes in front and here. When you divide 10 by 7, it will go once, and the remainder is 3. So the next step you write 7 comma 3. I hope it's clear. Then so in the next step, the 3 comes in front, so 3 comes here. And when you divide 7 by 3, it goes twice, and the remainder is 1, so 3 comma 1. Then after 3 comma 1, the 1 comes in front, and 3 divided by 1, there's no remainder. So the remainder is 0, and that's the end of the algorithm. You stop here, and whatever number is in front here is the highest common factor. So in that case, the highest common factor is 1. Now, what does it mean? So now we just retrace. So this 1, so let's see, from this relation, now let's look at this relation. We'll start with this, because we ended with a 1 here. So when you divide 7 by 3, it goes twice and 1 remainder. So 7 is equal to 2 times 3 plus 1. So I've written 1 is equal to 7 minus 2 times 3. That comes from this. Then, where did I get the 7 and 3 from? The 3 comes from 10 minus 7. So 10 is equal to 1 times 7 plus 3, right? So instead of writing 2 times 3, I'll write it as 2 times 10 minus 1 times 7. Now simplify that. So there is a total, if you look at the 7s, there is 2 times 1, that's 2, and then 2 negatives make a positive, so that altogether 3 times 7, so 3 times 7, and then minus 2 times. So you'll notice I've got 3 times 7 minus 2 times 10, and I've expressed a multiple of this, added to a multiple of this with negative numbers, it gives you 1. So the solution is x comma y is equal to negative 2 comma 3. So this is the Kottaka algorithm applied to this particular pair. Now you may wonder how come Aryabhatta was interested in this question at all. And the answer is that his interest came from astronomy. It was not actually to solve a recreational problem. It was to study, it came from astronomy. And why astronomy? In astronomy, or rather in astrology, people are very interested in occultation, when one object hides another. So suppose 2 objects are either one hides the other, or they are very close in the sky. Then after a few days, they diverge. So each one is going at a slightly different period, so they diverge. But after some time, they again come together. Can you predict exactly how many days or how many months or weeks, whatever, it takes to come together after starting out at one point having come together? That is, you can find the time period of the occultation. So this, if you solve this problem, it is actually the same as the problem of ax plus by is equal to 1. It's essentially the same. Now you can solve the jugs problem using this. Supposing instead of, I had shown you a situation where there is 3 and 2, or, sorry, I forget the original numbers. Let's suppose that the jugs had capacities 10 liters and 7 liters. Now we have just found that 10 times negative 2 plus 7 times 3 is 1. So I'm going to show how this gives you a solution to the jugs problem. So the positive 3 means it's associated with 7. So the 7-liter jug must be filled exactly 3 times. And the 10-liter jug, the 10 corresponds to minus 2, should be emptied twice. So let's see how this is done. So here's my notation. So I start with 0, 0. That means both jugs have got 0 in them. Then I fill I'm using this notation u comma v, which says that the 10-liter jug has got u liters, and the 7-liter jug has got v liters. So from 0, 0 you go to 0, 7. That means you have filled the smaller jug. Then you transfer the 7 to the bigger one, so you get 7, 0. Then again fill the 7 jug, so you get 7, 7. Then again transfer from here to here, so this becomes 10 and 4 is left over. Then you get rid of the 10, put it back into the tank, so this becomes 0 and 4. Then transfer that 4 to here, so 4, 0. Again fill the 7, so 4, 7. And then pour the 7 into this, so there's a deficit of 6 here, right? So this will become 10, and you'll be left over with 1 out here. Empty this 10 back into the jug, back into the tank, you'll be 0 here. So you'll notice that the 7-liter jug was filled 3 times, once, twice, thrice, 3 times. and the 10-liter jug was emptied twice here. So that corresponds to that +3 and -2. All right. So I just wanted to show you how this interesting algorithm, the Kotaka, plays a part here. And has anybody guessed which movie this is? I'll tell you again later. Okay, the last part of my presentation, if we have time, is about Brahmagupta triangles. Now, this is a problem which not associated with any practical problem at all. But to me, that tells me something very important, that the ancient Indian mathematicians loved mathematics for its own sake. They were not just interested in applying the mathematics to particular problems, though of course they did apply it, but they also loved numbers, and Brahmagupta was one of the first mathematicians who seemed to love numbers for their own sake. He would just, generate problems in which the solution was a huge number. Okay, so let's take a triangle with sides 3, 4, 5. Right? It will be a right angle triangle, and you can see that it has integer sides, of course 3, 4, 5. It also has integer area. It's right angled, 3 and 4 are its legs, so the area is half of 3 times 4, which means 6. So both its area and sides are integers. Such a triangle is called a Heron triangle, after that Heron's formula. Now, a particular case of a Heron triangle is a Brahmagupta triangle in which the sides are not just integers, but they are consecutive integers, like 3, 4, 5, that itself is. And in the 7th century, Brahmagupta found lots of such triangles. And for example, 3, 4, 5. He also found that 13, 14, 15 is a Brahmagupta triangle. I have not done the calculation here, but if you calculate it, you'll find that the area of this triangle is also an integer. Then he gave 51, 52, 53, then 193, 194, 195, and the numbers become bigger and bigger. And you may wonder, how did Brahmagupta possibly find such a, how did he manage to generate all these numbers? So obvious questions are, how did he find them? Is it possible to determine all such triples of consecutive positive integers? And are there infinitely many such triples? Very interesting number theory problem. So let's see how it can be solved. Suppose you call the sides of the triangle as a minus 1 and a plus 1. Here a is at least 3, it's some positive integer. So if you add up these 3, you get 3a. So the semi-perimeter is 3a by 2. And therefore, by applying the theorem of formula of Heron, you get the area B is s times s minus a and so on. So b squared times 3a by 2 times s minus, you get this expression. If you simplify this whole thing, you will find that you get this equation. 16b squared is equal to a squared times 3 times a squared minus 4. So since this is a perfect square, it's just 4b whole squared, and this is also a perfect square. So this must be a perfect square, 3 times a squared minus 4. So that's what I've written out. So put it equal to 3 squared. So just putting everything on one side, that is, we must solve this equation. A squared minus 3c squared is equal to 4. And if you actually start jumping forward by several into modern times, supposing you use computer software to generate solutions, just write a Python code, you can generate solutions to this. You'll find you get all the solutions which Brahmagupta had. A can be 4 or 14 or 52, 194, and then you get some more, 724 and so on. And you'll find there's a very nice recurrence formula which you get. You'll notice 52 is equal to 4 times 14, sorry, what have I written here? 4 times
minus 4.
Sorry, I think I made a mistake out here. 4 times 14 is, 4 times 14 is 56, minus 4 is 52. Yes. Then 52 times 4 is 208, minus 14 is 194, and so on. So you'll get, and both of them show exactly the same recurrence. 30 is 4 times 8 minus 2, 112 is 4 times 30 minus 8, and so on. Now, you may wonder how we get this out here. So if you if you do this analysis, I won't do the full analysis here, but it's easy to show that both A and C must be even numbers. If you look at that equation, it's easy to prove that A and C in this equation must both be even numbers. And you end up getting an equation like this. When you put A is equal to 2x, C is equal to 2y, so you get x squared minus 3y squared equal to 1. This kind of equation today is referred to as a Pell equation, but actually it is named wrongly because it was investigated long back before this European mathematician called Pell. It was investigated by Brahmagupta himself. And so it's more properly, you should call it the Brahmagupta-Pell equation. And he studied them in depth. And he found a very beautiful law of composition governing the solutions of these equations. And he gave it the name Bhavana. This Bhavana operation is a miraculous operation, and it's an idea which is unique, given that he was in the 7th century CE to get such an idea which belongs it's a very modern mathematical idea, 20th century idea. So his idea was, if A, B is a solution of this equation and CD is another solution, you can compose them, you can invent an operation, which we have just used this symbol here, A, B, C, D, gives you AC plus 3BD, comma, AD plus BC. We just use these numbers to get another pair, and it turns out that this pair also satisfies this equation. So Brahmagupta proved this. And using this idea, and he just keeps on using the same idea again and again, and you can get as many solutions as you want to the equation. So for example, you start with 2, 1. 2, 1 is a solution, right? X squared minus 3y squared. If you put x equal to 2, y equal to 1, it solves. So compose 2, 1 with itself. So 2, 1 composed with 2, 1 gives you 7, 4. Now 7, 4 double 7 is 14. So this triangle you get is 14, 14 minus 1, 14 plus 1. Then you can compose the solutions. Having got 2, 1, you can compose 7, 1 with 2, 4. So 7, 1, 2, 4, if you apply that formula, you will end up getting 26 and 15. 26 double is 52, so you get 52, 52 minus 1, 52 plus 1, another Brahmagupta triangle. And you can get infinitely many such things. So I won't say more about this. It's one of the great chapters. You can call it almost one of the crown jewels of ancient Indian mathematics, the exploration of this law of composition by Brahmagupta. And in later centuries, the idea was developed still further by the great Bhaskaracharya, the writer of the Lilavati. And in very recent times, that idea has been still further taken forward by a gigantic amount by the mathematician Manjul Bhargava, Indian origin American mathematician who got the field medal just a few years back. He's one of the top mathematicians around today. He has found some beautiful results related to the Bhavana. So that's all I want to share today. I want to just say this in conclusion. You might ask, what is the value of studying topics from our ancient past? Why study topics of this kind, whether it's the Bhavana or 4x4 magic squares or the Aryabhata's Kutaka algorithm? Does it have any significance? And to me, the answer is very simple. It is this. It's a line from Keats. A thing of beauty is a joy forever. Its loveliness increases. It will never pass into nothingness. So there is beauty in these results, and that is why we need to study it, not because of anything else, but because it is beautiful. And I think our lives need beauty. Our lives need that kind of touch. So that brings me to the end of the talk. I have shared with you some gems from ancient Indian mathematics, and I hope we have been able to experience their beauty together. Thank you.
ग्रेट डॉक्टर साहब, ग्रेट डॉक्टर शिराली, इंटरेस्टिंग। ऐसा लग रहा था कि सुनता रहूं, ये टॉक ख़त्म ना हो। आपने कहाँ कोटक कुटक्का का वर्ड का एक्सप्लेनेशन दिया, मज़ा आ गया डॉक्टर साहब. Really started with the mathematics is natural, mathematics gives you patterns. As in this context, people like me, I also belong to that school of thoughts. They say that mathematics is the first thing which a child starts learning after the birth.
Right.
This is and my saying is just on the basis of the understanding the patterns. The smell is also a part of pattern. Yes, Dr. Saab, you said that about that why should we study. Towards the end you finished with the beauty. For me it is a matter of confidence as well. If I know my past, if I know that my culture, my society has done so much in this, so I earn a confidence. And yes, there is the famous proverb case, I forgot that who says it, but nevertheless it goes like this, that the perfection makes us to gives the beautiful things, but at the same time the confidence gives us to be prepared for the worst. Yes, so this is another beauty. You talked about the symmetries, and then finding conjectures through the symmetries. I see symmetry in the sense that all laws of conservations, all laws of motion have emerged through the symmetrical studies, symmetrical observations in the nature.
Yes.
Yes, so I mean I was really trying to connect. I am a student of physics, so I was trying to connect each line of your deliberation, be it in the magic squares or be it in the jug problem or be it in Fibonacci numbers. But I see, can you take out your 26, slide number 26, slide number 26 in the second problem on Fibonacci numbers.
Yeah.
So that slide says the sequence and makes a photo of it's not that where you had putting the numbers. Let me yes, where you are having syllables, no, S and L.
Oh, that one.
Yes, yes. This is
This
the problem.
one?
Yes, this is the one. This shows us the total of the genesis of the
That's right.
Fibonacci numbers. But
That's right.
when you started the Fibonacci numbers, it started from 0, 1, 1 and so far so on.
That's right.
In this list, I do not find the first two integers, first two members of this.
So it's not. This is not a pure Fibonacci sequence. That's why I've written out here. It's a displaced Fibonacci sequence.
Oh, I see.
It starts from. That means the numbers 0 and 1 get left out. So it's a displaced sequence. So what we are trying to prove is that all these numbers are Fibonacci numbers, but even though there are some which have been missed out. That's what we prove.
Okay.
So that's how that proof goes. Yeah,
Okay.
you're quite right.
Yes.
It doesn't start with the same numbers as the Fibonacci sequence.
Yes, there are many questions. One more question I would like to take for the interest of the people, those who are working in allied areas of science. One child is asking about what is the connection of fractal geometries with these symmetries. Can you highlight?
Well, it's an unrelated topic, but see, fractals are basically structures which have self-similarity, in which a portion of the object or a subset of the larger object is completely geometrically similar to the larger object. And you'll find that these objects often have very, very deep symmetries of a very complicated kind. It would make one would have to make a different talk altogether, but they are mathematical structures which are produced by infinite processes, in which processes of contraction and expansion, where you get a new object which is similar to the original one, but at a different scale. So that kind of an object you can get only through application of some infinite process.
Yes, Dr. Shirali, yes, you have said it right, that it requires another full session to explain these expansions and similarities into that. But a connection probably the child was asking is in terms of the symmetries. Such an object can have very
complex symmetries. It can have symmetries which are reflection symmetries. It can have rotational symmetries. It can have. It can also have contraction and expansion, that is scale symmetries, which are not possible in ordinary geometry. So they are very interesting symmetries in fractals, which you don't encounter in ordinary course of events.
Right, sir.
So thank you, sir. We are running short of time now. I request.
Okay.
सर दरअसल सेशन ऐसा था, जैसा अभी गगन सर ने भी कहा कि समय की अपनी सीमाएं हैं, लेकिन आपने जो प्राचीन भारतीय गणित के उदाहरण हम सबके साथ साझा किए, उसके लिए वाकई में और समय चाहिए, और आपने जितनी भी मेहनत की है, मुझे लगता है आपकी जो रिसर्च है वो हम सबके बहुत काम आने वाली है। बहुत ज़्यादा इंटरेस्टिंग था पूरा सेशन, उसके लिए आपका बहुत बहुत धन्यवाद, बहुत आभार, आप हमारे साथ जुड़े। थैंक यू वेरी मच।
बहुत धन्यवाद। गुड बाय।
और मैं अपने सभी दर्शकों को भी ये बताना चाहूँगा कि हमारा आज का ये जो सत्र है, ये 44वां सत्र था जो कि समाप्ति की ओर है। अगला सत्र 45वां सत्र जो है वो रेडियो तरंगों से ब्रह्मांड का अन्वेषण, इस विषय पर आधारित होगा। और जो हमारे गेस्ट हैं उनका भी परिचय मैं आपसे बता देता हूँ। यशवंत गुप्ता हमारे साथ होंगे, नेशनल सेंटर फॉर रेडियो एस्ट्रोफिजिक्स, टाटा इंस्टीट्यूट ऑफ फंडामेंटल रिसर्च, पुणे से। तो वेबिनार सीरीज लिसनिंग टू लर्न देखना ना भूलिएगा। अगला ये सेशन हमारा 25 तारीख को होने वाला है, 25 नवंबर 2022। गगन सर, आपका भी मैं बहुत बहुत धन्यवाद कहूँगा कि आप ये जो अपना होमवर्क करते हैं, हमारी ये जो वेबिनार सीरीज है इसको आगे तक ले जाने का जो आप काम कर रहे हैं, उसके लिए बहुत बहुत धन्यवाद, बहुत आभार।
थैंक यू व्यूअर्स, आप सबका बहुत बहुत धन्यवाद है। आपसे फिर पुनः मिलेंगे 25 नवंबर को। धन्यवाद।
और जैसा कि गगन सर ने आपसे पहले भी निवेदन किया था कि आप अपने जो सुझाव है वो ज़रूर हमें भेजिएगा, ताकि हमारा ये जो कार्यक्रम है और हम इसे बेहतर बना सकें और आपके लिए और बेहतर चीज़ें लेकर आ सकें। फिलहाल मुझे और मेरी पूरी टीम को दीजिए इजाज़त। हमारा ये सेशन यहीं समाप्त होता है। नमस्कार।